Welcome friends, I am Vijay Shankar Dwivedi, TA in this course. In this week, in previous lectures, you have studied about the spring, mass and damper system, and you have visualized that you can understand all modes of the aircraft with the help of this spring, mass and damper system. In today's lecture, we will be solving few numericals. Before that, let us take a review of the what we have studied in the previous classes. In the spring, mass, damper system, we have three basic elements. The first one is the mass. Whenever we apply a force on a body, the opposing force and the applied force, the net summation of them is 0, and due to the mass there is opposing force, and this is the inertial force. And suppose we are applying a force here Ft, there will be a inertial force realized on this mass, and this will be, from the Newton's second law, we can write mass into acceleration, or we can write it m dv dt if this is the v of t, or if we talk in the terms of displacement, this is x of t, and this is equal to m d square x of t by dt square, and this is conservative in nature. Basically, it stores the kinetic energy of the system, and we can retrieve all the energy without any loss. And the second term, and the second element is the spring. This also applies a restoring force. Suppose its spring constant is K, the restoring force due to the spring is K x of t if the displacement is x of t, f of spring. The x is the stretching in the spring. If spring is connected in such a fashion that its both terminals are getting some displacement, suppose this part is displaced with x1 of t, and this part is getting displaced with displacement x2 of t. So, the force applied due to this spring will be, if the K is the spring constant of this spring, then this will be K x2 of t minus x1 of t. The relative change in the length of this spring. And the third element, the spring is also conservative in its nature, and it stores the potential energy of the system. So, the spring and mass both are transferring the energy of each other with the phase difference of 90 degree. But you can see here the energy is conserved throughout the process. So, if there is a spring mass system and if you deflect it, it will continue oscillating because there is no any energy dissipating element. And the third element is the damper. Damper is basically non-conservative in nature. It dissipates the energy from the system to the environment, and it works basically on the friction. And in the nature there are three types of friction. The one is static friction, f of s. The static friction is when we apply on the force on a body just before the movement we realize this friction. Once the body starts moving, this friction disappears, and if I plot it, it will be something like this. Suppose this is the x axis is the velocity axis and this is my friction f of s. So, it is something like this. Whenever there is the velocity, it will be 0. And the second type of friction is viscous friction. And this friction is whenever a body moves in a fluid, we realize this friction, and in our discussion most of the time we visualize this friction. So, f of b is equal to b into v, and if I plot it, it will be like this, and the slope is p. And the third type of friction is the Coulomb friction. This is constant in nature, it is like once the object starts moving, a constant force is applied on the body, and whatever the value of the velocity is, it will remain constant. In our study, most of the time the friction we observe is the viscous friction. So, we will be ignoring the static friction and Coulomb friction, and the friction that we will observe is the viscous friction only, and the force due to this friction is the b into v, or we can write b into dx of dt. And whenever the force is proportional to the rate of change of displacement, it will have a inherent tendency to dissipate the energy from the system to the environment, and this will cause damping. That is why you call it damper also. Now, let us have a look of spring mass and damper system. Suppose we have a spring and this is attached to a mass m. We apply a force here f of t. The displacement is x of t, and the spring constant of this spring is k. So, when we apply the force f of t, the net force, the opposing force and the applied force, they will be equal. So, we can write f of t is equal to m d square x of t. This is the inertial force and the force due to the spring. So, these both forces, this inertial force and this spring force, both are conservative in nature. That is why this will keep oscillating, and if I solve this differential equation, I will get the solution in the form of sine and cosine. Suppose I have the spring constant of value 32, spring constant of 32 and mass of 2 kg. You can see its response plotted in this plot. Amplitude of the oscillation is not decaying with the time. So, this we call the undamped motion. The time difference between the two consecutive peak is constant throughout the oscillation. So, its frequency is constant, and this frequency we call the undamped natural frequency. Now, let us see if we attach a damper in the system, then how it is going to change the dynamics of the system. Suppose this is the spring and one mass is attached to this, it is 2 kg and the spring constant K is 32 and there is a damper and its value is, suppose it is 2. Now, you can see in this plot the amplitude of the oscillation is decaying with the time and it is due to the damper has inherent tendency to dissipate the energy of the system through the environment. That is why the energy of the system is decreasing and the amplitude of the oscillation is also decreasing with the time. And here also you can see the difference between the two consecutive peaks is constant and this we call the damped natural frequency or damped frequency. Now, I can write its equation of motion . This is B. You can write C also, both are same. If I write its characteristic equation, it will be m x double dot plus b x dot plus k x is equal to 0. This is the characteristic equation of this differential equation, or I can write x double dot plus b by m x dot plus k by m x is equal to 0. If I see the roots of this equation, the roots are given by minus b plus minus root over b square minus 4 k m by 2 m, and this will be minus b by 2 m plus minus I omega d, and this omega d we call the damped frequency. Omega d will be given by under root b square minus 4 k m divided by 2 m. Now, for the b is equal to 2, our b square minus 4 k m, b square will be 4 and 4 k m is 256. So, b square is less than 4 k m. This 4 k m is negative, we get imaginary roots, and in that case this is damped frequency. Here in this curve also you can see the amplitude is decaying with the time and the difference between two consecutive peaks is constant, and the inverse of that will give us this omega d damped frequency. We can calculate by putting this value also. Now, if I increase the value of this damping coefficient from 2 to 8, in this case this will be 64. In this case also this this term b square minus 4 k m will be negative and this roots will be imaginary, and we will get under damped motion, and here also you can see the damping is more, but still it is under damped, and the curve is overshooting mean position and again coming back to its mean position. And if I further increase my damping ratio from 8 to 16, and in this case this will be 256 and this part will be 0 and this will be a negative term. In this case we call it critical damping, and here you can see there is no overshoot, and with the increase in the damping, the first time when the overshoot disappears we call it the critical damping. There is no oscillation in the response, and if I further increase from 16 to 32 and so on, then we will have higher and higher damping, and this situation we call the over damped response. If I try to visualize my longitudinal motion of the pitch only motion of the aircraft, if you remember the equation, I y by q dot is equal to half rho v square s c bar multiplied by Cm alpha into alpha plus Cm q into Qc by 2b plus Cm alpha dot into alpha dot C by 2b plus Cm delta E into delta E. And here you can see this is basically mass into acceleration, this is inertia and this is the rate of change. So, this is the force, and if you see in the right hand side, if I multiply this half rho v square s c bar with these terms, here the Cm q will have a velocity term into the multiplication, because this square will be cancelled with this velocity, and similarly with the Cm alpha dot also. So, you can see Cm q and Cm alpha dot, these two terms producing a moment on the aircraft which is proportional to the velocity, and that is why ultimately this will act as a damper. This will be generating the damping effect in the pitching motion. If I see the top view of one airplane, when there is a pitch rate, this horizontal stabilizer will have a tendency to oppose that change in the pitch, and due to this force we get this Cm q. And similarly, when my aircraft is moving like this, and suppose I am here, suppose this is the velocity of the aircraft, when my aircraft was moving in this direction, that time if I had the angle of attack, for example 3 degree, and when it will be moving here, then this angle of attack will be increased to some higher value, and due to this increase a moment will be realized on the aircraft, and this will try to oppose the change in the pitch, and this is proportional to the velocity. So, ultimately it will try to damp that oscillatory motion about the mean position of the aircraft. Now, let us solve one numerical. A system is described by a differential equation d square y of t by dt square plus 8 dy of t by dt plus 25 y of t is equal to 50 x of t. Now, we have to find omega n, undamped natural frequency, omega d, the damped natural frequency, and damping ratio zeta. So, if I take the Laplace transform of this equation, I can write s square y of s plus 8 sy of s plus 25 y of s is equal to 50 x of s, and I can write s square plus 8s plus 25 50 x of s, and from here y of s by x of s can be written as 50 by s square plus 8s plus 25. I can write from here the characteristic equation. S square plus 8s plus 25 is equal to 0, and now if I compare with the standard equation s square plus 2 zeta omega n s plus omega n square is equal to 0, then if I compare these two equations, I can find omega n square is 25, so omega n is equal to 5. So, the omega n will be 5 radian per second, and 2 zeta omega n is equal to 8, zeta omega n is equal to 8, omega n is equal to 5 radian per second. So, I can write zeta is equal to 8 divided by 10, so it will be 0.8, and the omega d, we can write omega d omega n root over 1 minus zeta square, and from here we can, the omega n is 5 radian per second and root over 1 minus zeta square, zeta is 0.8. So, 1 minus 0.8 square is 0.64, 1 minus 0.64, 0.36, so 0.6, and omega n is 5, then 5 into 0.6 is, it will be 3 radian per seconds. Now, coming to our next numerical, a system is described by y double dot minus 5 y dot plus 6 y is equal to 0, and we are given the initial conditions y 0 is equal to 2 and y dash of 0 is 2, and we have to find y of s and y of t. So, by taking the Laplace transform, we can use the formula, the Laplace transform of d square y of t by dt square is given by s square y of s minus s y of 0 minus y dash of 0, and the Laplace transform of dy of t by dt is given by s y of s minus y of 0. So, by using these two formula, we can write s square y of s minus 2s s y of 0, and y dash of 0 is also 2. So, minus 2 minus 5 y dash 0 s y of s minus 2 and plus 6 y of s is equal to 0. And if I separate the y of s from this equation, I will get s square and minus 5s plus 6 and the remaining terms minus 2s minus 2 and plus 10 is equal to 0, and from here we can get y of s square minus 5s plus 6 minus 2s plus 8 is equal to 0. So, finally, we can get y of s two s minus 8 divided by s square minus 5s plus 6. And now, if we break it with the partial fraction, the s square minus 5s plus 6, we can write it this term s minus 2 into s minus 3, and if I break it into the partial fraction, I can write it is equal to a by s minus 2 plus b by s minus 3, and if I determine the value of a by putting the s is equal to 2 and eliminating this term, I will get 2 into 2 minus 8 divided by minus 1. So, this will be 4. So, I can write is 4 by s minus 2, and now the b, I put s is equal to 3 and I eliminate this term, then I will get 2 into 3 minus 8 and 3 minus 2. So, this will give me minus 2 divided by 1. So, this will be minus 2. So, this is my expression for the y of s, and the next part is what is y of t. So, if I take the inverse Laplace transform, I will get y of t is equal to 4 e to the power 2t minus 2 e to the power 3t. Thank you.